With the advent of Vivado HLS, we were living in a new era. Being able to use C as the input language for your design was opening the access to the FPGAs to an entire new set of people, which was great because it was also bringing new challenges to be solved. We were now assisting to a scenario where non-FPGA experts were interested in using them, but with a complete new approach to the design. For us, this was a super exciting time. There was the need of a method to manage complexity and dynamism. We had to define ways and tools that let users and developers specify and formulate desired behaviors rather than fix immutable solutions to be implemented. Moreover, from an EDA perspective, there were several techniques to exploit partial reconfiguration, but few approaches for frameworks and tools to design dynamically reconfigurable systems. No support for a design that was using different devices. Within this context, we work in the ASAP research at the definition of a methodology for the design of dynamically reconfigurable FPGA applications. From a research perspective, this implied the ability to identify and implement the area constraints for the reconfigurable cores. In other words, the identification and definition of the reconfigurable regions. To provide guidelines on the identification and definition of reconfigurable cores. To define the module schedule, trying to reduce the reconfiguration time. To manage the runtime swap of reconfigurable cores. We were considering FPGA as a viable prototyping platform to study, design, and verify novel adaptive computing architecture. This has been done in the change research by the definition of mechanism to monitor the system and the environment, and to collect the information necessary to compute the measures to define the goals. The definition of the general runtime optimization and adaptation mechanism to be embedded in the system that observe the execution, measure thresholds, compare them to goals, and then modify the architecture and the operating system or the algorithm as needed. The design of the hardware runtime mechanism to perform the reconfiguration and/or the evolution of the system. From a design framework perspective, the work done in ASAP was enhancing the previous DRESD research because we introduced a high-level languages support. We did this by creating an interface in between our toolchain and Vivado HLS. We were no longer focusing only on embedded system on chip, but we were taking into consideration also host-based systems. We introduced an automatic reconfigurable course candidates identification and an automatic reconfigurable regions definition. The automatic reconfigurable regions definition was, and still is, really useful, not only for the reconfigurable regions identification, but also because we were providing suggestions and feedbacks on how to solve unfeasible reconfigurable regions constraints. Finally, we started to work on a set of API to allow the integration with other reconfiguration-oriented flow, such as the micro-reconfiguration created by Professor Dick Stroban of the Ghent University. Just to give you an idea of why it is important to be able to properly identify the reconfigurable regions. Let us consider the following two designs. Which one do you think will be the best one? Well, first of all, we may have to define best with respect to what. We may take wireland or area as the figures that have to be optimized. Well, from a pure aspect ratio perspective, I pick the one on the left. The one with the big square region on its bottom right corner. Well, if you did the same, you picked the wrong one. The best one is the one on the right, and the reasons are quite simple. It has 34% wasted frames reduction, guaranteeing the same runtime. No DSP, CLBs or BRAMs wasted inside the identified reconfigurable region, and approximately the same wire length of the other solution.